Hi, hello, welcome back. And we will be continuing our discussion regarding the AC analysis for BJT transistor. Okay, so just for a review, for our review from our previous discussion, so we are going to start with our AC analysis by redrawing, okay, our schematic diagram, our main configuration to its AC equivalent circuit. So for a review, how are we going to do that? Okay, so since we are only interested with the AC source, and in that case that is your VS here. This is our AC source, so we have to turn off our VCC here, which happens to be a DC source. So how are we going to um, remove the effect of our DC source in this configuration? So we are going to make your DC supply at zero potential, so that means we're going to ground. Okay, so we're going to short this VCC, so we're going to replace this with a short circuit. And then in DC analysis, these three capacitors here acts as an open circuit, but in AC analysis they will be replaced by a short circuit. So how many short circuits are we going to have? So we're going to have our first short circuit here for our input coupling capacitor, our second short circuit here as our output coupling capacitor, and the third capacitor is to bypass the effect of our RE. So later we will see the effect of RE if we do not bypass it and if we bypass it. Okay, so we're going to make your bypass capacitor C3 here equivalent to a short circuit. So upon doing those things, upon shorting your DC source and your three capacitors here, our schematic diagram, our complete schematic diagram will be or will look like this. Okay, so VCC is shorted, and then the three capacitors are replaced by short circuit. So this is now the redrawn voltage divider configuration after removing your DC supply and after inserting short circuit in lieu of your three capacitors. Okay, so last video we also discussed that we can redraw this specific circuit. So this will look like this one, and then we're going to model your transistor here. Okay, so as mentioned from our previous video, there are two models available for our BJT transistor. So that is your RE model and our hybrid model. So in this video, we will be discussing the difference between the RE model and the hybrid model. Okay, so for this discussion, we are now going to replace. So this is short transistor. We use this in your DC analysis. However, we will be getting the equivalent circuit for your transistor. Okay, so how are we going to model? How are we going to get the characteristic of this transistor here? Okay, so our modeling of the BJT begins here. So we have two types of model. It's either the RE model and the hybrid model. Okay, so just for a recap, AC bias analysis, what are we going to do? So you have to kill all your DC sources. You have to replace your coupling and bypass capacitors by their equivalent short circuit. Okay, so the effect of these capacitors is to set a lower cutoff frequency for the circuit. But this second statement here will still be reflected on our electronics too. Okay, and then we're going to inspect the circuit. So we will be concentrating on this part. We're going to replace your BJT in its small signal model. So it's either RE and or hybrid. And in each model, we will be trying to solve for the four important parameters. Okay, so what are those four important parameters as discussed also in the previous video? So that will be your input impedance, your output impedance, our voltage gain, and our current gain. So we will be discussing, or our computations or our analysis will be based or will be focused on those four important parameters. Okay, so we will be starting first with the RE transistor model. So the RE transistor model employs a diode and a controlled current source to duplicate the behavior of a transistor. So your BJT transistor will be represented. So it will be modeled by a diode and by a controlled current source. So in your circuit analysis, we have a current source and we have a controlled current source. So that means that the current flowing across that current source is somewhat controlled by another current from another part of your circuit. Okay? So BJT BJTs or BJT amplifiers are referred to as current controlled devices. That's why in their model, in their transistor model, we can see a controlled current source in the symbol. Okay, so we will be starting first with the common base configuration. So we will be dealing with a common base BJT transistor. How does its RE model looks like, and what will be the RE equivalent circuit? Okay, so this is the common base BJT transistor. So this is a PNP configuration. So if we will be using an NPN configuration, all we have to do is to just uh, reverse the direction of this current. Okay, so this is a PNP transistor. By looking at the symbol, your arrow symbol is pointing in, and then wherever your arrow is, that is your emitter, and the other terminal is your collector. So this is a common base configuration because as you can see, your base is common to both your input and your output. So the input is between the emitter and the base, while the output is between the collector and the base. Okay? So as mentioned in the previous slide, the model, okay, for the RE model for a common base configuration is represented by a diode. So this is our diode. So the diode represents the input side. So what is the input side? It is between the emitter and the base, while the other one, the output side, is represented by a current controlled. Okay, so this is our symbol for a current source. Okay, so our symbol for a current source is an arrow, and wherever your arrow is pointing, that will be the direction of your arrow. So since the output for a common base is the collector, therefore, we are having here your collector current. However, since this is current control device, which controls your collector current. So your collector current is being controlled by an input current, which is your emitter current, multiplied by our alpha here. So as mentioned before, alpha is being seen when we are implementing a common base configuration. So why is this called current controlled current source? Because your IC is dependent on your emitter current. Okay, now notice our subscript, our letter subscript. So as you can see, they are all written in lowercase letters. No, so why are they written in lowercase? Because we are now dealing with AC analysis. Okay, so that's why they are written like that. So we have here the RE model for a PNP common base configuration. So this is your schematic symbol, the transistor itself. So the transistor can be modeled as a diode and a current source. Okay, so this diode here can be represented by a resistance RE. Okay, so what is this specific RE? So as we all know before in our prelims that your diode has an AC dynamic resistance. So the resistance across your diode is our RE. So how are we going to determine your RE? So as we can see, the emitter here is not connected to the collector here. So we are isolating your input side and your output side. Okay, so your RE now will be the basis for our input resistance. Remember, we have four important parameters, and the first important parameter is the input impedance. Okay, as you can see here, can you notice any other impedances or resistance at the input side? So all we see is your RE. And what is RE? RE is equivalent to 26 millivolts divided by IE. Look at the subscript. It is written in capital letters. So what do we mean by a capital letter? So it means it is a DC value. Okay? So IE here is the DC level for your emitter current. Now, are you familiar with this formula? So this formula, 26 millivolts divided by the emitter current, is our approximation for your AC dynamic resistance. So if you can still remember in our prelim study regarding the diode, so we can compute for the AC dynamic resistance using a tangent line, if you can still remember. However, we can have an approximation. So we can compute based on its slope. And we have derived this formula, which is 26 millivolts divided by IE. So in this case, we can see that the DC analysis part is very important in the AC analysis part in getting or in solving for your RE. Why? Because we need to solve first for your IE. So how do we solve for IE? So we will be going back with your previous video regarding the DC analysis. Okay, so therefore, the input impedance or ZI is equal to RE. So usually, RE is a very, very small value. So the AC dynamic resistance for a diode is a very, very small value. So the ideal value for this is 0 ohms, but in reality, so it is usually a value which is lesser than 50 ohms. Okay, so our first important parameter for a common base configuration is our input impedance, and our input impedance is equal to RE. So for the second important parameter is the output impedance. Okay, so how do we solve for the output impedance? So the output impedance is being taken when we are killing your input source. Our input source is Vs. So what do? We short your Vs. So we make it equal to 0 volts. So if that is equal to 0, therefore, your IE here is also equal to 0. But since our IC is dependent on IE, that means when your IE here is equal to 0, likewise, your IC is equal to 0. So what do we mean by a zero current? So a zero current means an open circuit. Therefore, we have an open circuit here. Now, what resistance can we read or can we find when we have an open circuit? Okay, so the resistance in an open circuit is always equal to infinite. Okay, so therefore, for a common base configuration, our ZO is approximately equal to infinite, or it is a very, very high value. Okay, so we have already taken two important parameters. So the input impedance is equal to RE, and the output impedance is equivalent to infinity. So this is the common base characteristic. So the input relating to the output. So the input current is IE and the output current is IC. So as we can see, they are approximately equal. Why? Because your base current is always very, very small compared to these two currents here. Okay, so for a BJT common base transistor amplifier, we are now going to define your voltage gain. So what is your voltage gain? Voltage gain is equivalent to output voltage divided by VI. So in getting that, since this is an infinite and this is your ZI, which is equivalent to RE, we place here a load resistance. In this load resistance, we're going to measure your VO. Okay, so what is VO? VO is RL multiplied by IO. But as you can see, okay, your current IO is of opposite polarity compared with our VO here. Because when your direction of IO is going here, going to the left, your VO must be positive and negative. However, our VO here is plus and minus. So that means we have opposite in the polarity. So when we have an opposite in the polarity, we can see a negative sign. Because if we're going to follow your IO, so if we're going to follow your IO, the direction of your IO, it should be what? In this circuit, it should be, if this is your RL and this is the direction of your IO, this must be plus and minus VO. However, our representation is plus and minus VO. So they represent an opposite in polarity. Therefore, we have a negative sign here. Okay, so the negative sign is because your IO is in the opposite direction. Okay, so going back, but what is IO? IO is also equal to your IC. Okay, but they have an opposite direction. So, since they have an opposite direction, we can represent your IO equivalent to negative IC. Okay, so if it happens that they flow at the same direction, so we don't have a negative sign there. So the negative sign here is because your IC is moving towards to the right while your IO is towards to the left. So since they are of opposite direction, we will be placing an IC here. But since IC is dependent on IE, we can say that your IC is also equal to alpha multiplied by IE. So we have minus sign here, we have negative sign here, so we have here positive. Okay, so what is VI? Your VI here is equivalent to IE, no problem, because of the direction of IE, it is the same with your VI here. So that is equivalent to IE multiplied by your ZI. But for common base, what is ZI? ZI is equivalent to RE here. Okay, so substituting our formula for VO all over VI, we have here alpha IE RL divided by IE RE. Okay, so that means we are going to cancel your IE here. So canceled, IE is canceled here. So what do we have here for our voltage gain is alpha multiplied by RL divided by RE. But what did we learn from our previous discussion? So we say that your alpha is approximately equal to 1. So its value is always lesser than 1, but it is approximately equal to 1. Why? Because your IC is approximately equal to your IE. Okay, so alpha is the formula relating your output current divide by the ratio of your output current, which is the collector current, and your emitter current. Okay, so we have here, so if we are going to assume this to be equal to approximately equal to 1, so we can have your voltage gain, which is equivalent to your RL divided by your RE. So we have here a ratio consisting of resistors, and yet we are solving for the voltage gain. So what is the unit for voltage gain? So the voltage gain is always unitless. Why? Because your RL is in ohms and RE is also in ohms. So your ohms will be cancelled out. Therefore, voltage gain has no unit. Okay, so we have your ZI, which is equal to your RE, and then you have your ZO, which is infinite, and then we have the voltage gain, which is equivalent to your load resistance divided by your RE here. Okay? And then lastly, we're going to define your current gain. So current gain is equivalent to I/O, output current divided by the input current. Okay, so the current gain for a common base is, what is your output current? Our output current is this one, that is also equal to your current gain, but in opposite direction. So we have here minus IC, okay? Divide by, what is our input current? Our input current is IE. But what is IC? IC is alpha IE. Okay, so therefore your IE here will just cancel out. So therefore, for common base configuration, our current gain is negative alpha. So if we're going to approximate alpha be equal to 1, so therefore the current gain for a common base configuration is equivalent to negative 1. So what does this implies, class? So this implies that in common base configuration, there is no really current amplification, because in reality, whatever your output current is, that is usually approximately equal or lesser than your input current. However, in common base configuration, we can see that we have a voltage amplification. Why? Because we say that RE is usually a very, very low value, lesser than 50 ohms, and RL is usually in terms of kilo ohms. So therefore, we have here a value which is larger than 1. So that means there is a voltage amplification for common base. Okay? So in common base, no current gain, but we have a voltage gain. So we have here a very simple example. So for a common base configuration in the figure below with IE, take note of your IE, it is capital letter. So why? This came from the DC analysis. So for example, we have already solved this problem and we found out that its DC current is equal to 4 milliamperes. So we have here our alpha, which is equivalent to 0.98. We have our input signal, so AC signal, which is 2 millivolts, and it is applied between the base and the emitter. So since it is applied between the base and the emitter, so it is equivalent to our input voltage. Okay, so we are to determine your ZI, we are to determine your ZO, and we have to determine your current gain. So we are going to determine your voltage gain if your RL is equivalent to 0.56 kilo ohms. Actually, class, this is just a direct substitution from our formulas. Okay, so we just have to substitute the value. So ZI is equivalent to RE, and RE is equivalent to 26 millivolts divided by IE. So since IE is already given, so this is equivalent to 6.5 ohms. As expected, it is usually a lower value of resistance. Okay, so for common base configuration, your voltage gain is equivalent to alpha RL divided by RE. So we didn't use 1. Why? Because alpha is given. So that is 0.98 multiplied by RL, which is 0.56 kilo ohms, divided by our RE, which is 6.5 ohms. So that will give us 84.43. So it is unitless. So what does this mean, class? So this means that your input voltage was amplified 84.43 times. Okay? And the absence of a negative sign here means your input voltage is in phase with your output voltage. So if this is our input voltage, so your output voltage is this one. Okay, so they have the same phase and it was amplified 84.43 times because of the absence of the negative sign. And then, what is your ZO? So for common base configuration, ZO is equivalent to infinity. So you have already an answer there. And your IO is equivalent to negative of your alpha. So that is negative 0.98. So what do we mean by the negative sign there? So the negative sign there implies that your output current is 180 degrees out of phase with your input current. Okay, so it was reduced by 0.02%. So, and it is 180 degrees out of phase, and that out of phase is being represented by the negative sign. Okay, so this is the common base RE equivalent circuit. So it is represented by your RE here, and then we have here your current-controlled current source. Okay, so the current IC is being controlled by your current IE. So we have another example for a common base configuration in the previous example with IE. Okay, take note. What's the difference between IE here? So your IE here is small letter, so lowercase. So therefore, your IE here is AC and not DC. So since this is not DC, we cannot use the formula 26 millivolts divided by IE. So we cannot use this. Why? Because the IE that we are given is one which has a small letter. So that means this is the AC current. Okay? And what we need for this formula is the DC current. So therefore, we will not be using that formula. So how are we going to solve for that? So ZI, what is ZI? ZI is your input voltage AC. So that is your input voltage AC divided by your input current I. Okay, so we have here, how do we solve for this? Since we are not given we cannot use that formula, we cannot use this formula. So we have here your ZI instead. Okay, so ZI is equivalent to, so what is your input current? Your input current is IE and your input voltage is 10 millivolts. So the AC signal which is applied. So we have here 10 millivolts divided by 0.5 milliamperes. So your ZI here is 20 ohms. So we will not be using the 26 millivolts here. Why? Because this is DC and the given current is AC. So we will just be using this ZI formula. So VO is equivalent to ICRL. But what is IC? IC is alpha IE multiplied by RL. So alpha is 0.98, IE is 0.5, and RL, given your load resistance to be 1.2 kilo ohms. So your V out is 588 millivolts. Okay, so in this case, you are given an input voltage, you are given an output voltage. We can solve for your voltage gain. So your voltage gain is your output voltage, which is 588 millivolts, divided by your input voltage, which is 10 millivolts. So your millivolts will be cancelled out, giving us a value of 58.8, which is unitless. So what does this mean? So this means that your input was amplified 58.8 times. So from 10 millivolts, it became 588 millivolts. Okay? And what is your AI? So from the formula, from the approximations, AI is equivalent to negative alpha. So that is equivalent to negative 0.98. Okay? So lastly, we are asked to solve for IB. So how do we solve for IB? So the formula, which is IE, okay, so IE is equal to IB plus IC. This still applies with AC analysis. Okay, so the only difference is in DC, we use capital letters, but your base current is your emitter current is still the sum of your base current and your collector current. So in this case, we have here your IB is equivalent to IE minus IC. Okay, so we have here IE. I is given 0.5 milliamperes, but we don't know IC, but IC is equivalent to alpha multiplied by IE. Okay, so we have here 0.5, factoring out your IE here. So you have 0.5, 1 minus alpha. Alpha is 0.98. So that will give you an IB, which is equivalent to 10 microamperes. So comparing the values for the three currents, still in AC analysis, your IB is still of the lower values among the three. So usually IB is in terms of microamperes, while your collector and your emitter current is almost equal, and they are in a milliampere range. Okay, so that's it, just a formula. Okay, now what about the common emitter configuration? So in our previous topics, we have seen a lot of common emitter configuration really. So we are interested in the common emitter configuration. So for common emitter BJT transistor, we will be trying to draw its RE model together with its RE equivalent circuit. So it is still made up of a controlled current source conducted between the collector and base terminal, and a diode conducted between the controlled current source is conducted between the collector and the base and the emitter. So this must be emitter, while the diode is conducted between the base and the emitter terminal. So in common emitter configuration, your input is the base and emitter terminal, while your output is the collector and emitter terminal. Okay? So in this example, so this is how your common emitter looks like. So this is your base, this is your collector, and this is your emitter. So this time we have a NPN transistor. As you can see, the arrow is not pointing in. However, if you are being asked to use PNP transistors, all you have to do is to reverse the polarity of or the directions of your currents, okay? So, the RE model for an NPN common emitter configuration is a diode between the base and the emitter. And we have a current-controlled current source between the base and your collector. Okay, so this is the RE model for an NPN common emitter configuration. So if we're going to separate your input and your output side, okay, so we are trying to determine your ZI using the RE equivalent model now. Okay, so your ZI, as you can see, where is your ZI? So that is the input impedance. Your input impedance is equivalent to VI divided by your I input. Okay, so what is our VI? Your VI is pointed with VBE. Okay, so we have a plus and minus VBE. That is the voltage across your RE, which is in parallel with your VI here. While your I input here is your base current. So the input current for a common emitter configuration is your base current. Okay, VI is equal to VBE, and that is also equivalent to IE multiplied by RE. Okay, so but what is IE? Actually, your IE, you can still remember, your IE is beta plus 1 multiplied by IB. Okay? However, we can approximately remove your 1 here because beta is much greater than your 1. Therefore, your IE is approximately equal to beta multiplied by IB. Okay, so replacing that in our formula here, you have beta IB multiplied by RE. Okay, so your ZI here is equal to VBE, which is beta IB multiplied by RE, divided by the input current, which happens to be your IB. So, canceling out your IB here, that will give us an input impedance, which is equivalent to beta multiplied by RE. So, what is the difference between common base configuration and common emitter configuration? So, the input impedance for a common emitter configuration is slightly higher or greater than your common base configuration. But the way we solve for your RE is the same. So it is also equal to 26 millivolts divided by the DC current, DC emitter current. However, we still have to multiply it with beta. So for a common emitter configuration, what is your ZI? So your ZI here is beta multiplied by RE. Okay, so ZI ranges between hundreds to 6 to 7 kilo ohm. So actually, it is very much greater than your input impedance for common base because of your multiplier here, which is your beta. Okay, so relating your input current and your output current here, we can see that they are not approximately equal because IB is much smaller compared to your collector current. So how about the output impedance? So what do we do for an output impedance? So we kill your input source. So when we kill our input source, that means we short it. Okay, so when your input is equal to 0, therefore your IB is equal to 0. So when your IB is equal to 0, since this is a current controlled, when IB is equal to 0, this is equivalent to a short circuit. Okay, so open circuit. And what is the resistance in an open circuit? Technically, it is infinite. However, for common emitter configuration, sometimes we have an output resistance. So this output resistance is not the resistor that you usually borrow from the laboratory. So it is within the transistor itself. So how can we know, or how do we know if what is the value of our output resistance, output internal resistance? So usually it is given in the specification sheets. So if it is not given, we're going to assume that this is just an open circuit. So if it is an open circuit, that means it is infinite. However, if we are given an RO, and since this is open, the only thing that we can see at the output side is your RO here. So your output impedance is equivalent to whatever the value of your RO. Okay? So if RO is ignored, if it is not given, therefore, we can say that ZO is equivalent to an open circuit or high impedance. So this is the difference also for common base and common emitter. So for common base, we assume right away that your ZO is infinite. Okay, but in common emitter, we have to be very, very sure if RO is really not given. So if it is given, we have to consider its effect. Okay, so determining the voltage and the current gain for a common emitter amplifier. So what is your VO? Again, the same as the same like our common base configuration. We have a negative IO here because it is opposite in the polarity for our VO. So you have your IO multiplied by RL. So the difference here is we no longer have a negative IC here. Why? Because you can see your IO has the same direction as with your IC. So since they are of the same direction, okay, so they have the same direction. So we have here simply beta IB. So IC is equivalent to beta IB. So that means the negative sign here cannot be removed. So your VO is really negative beta IB multiplied by your RL. So what is your input? So your input is equivalent to I input multiplied by your ZI. So what is your I input? Your I input is IB. Our ZI is beta RE. Okay? So, getting the gain now, VO all over VI. So, VO is beta IBRL. VI is IB beta RE. So, beta is cancelled out. IB is cancelled out. So, what do we have in our voltage gain? Voltage gain is RL all over RE. So, just like what you have in a common base configuration. The difference is what? We have a negative sign here. So what does this negative sign implies? So for common emitter configuration, your output voltage is 180 degrees out of phase with your input voltage. So what do we mean by that? It is amplified because RL has a much greater value compared to your RE. However, if this is our input voltage, your output voltage is like this. So they are 180 degrees out of phase. Okay, so that is your voltage gain. So again, these are two resistances. So ohms will be cancelled out, giving us a voltage gain which is unitless. For current gain, okay, so that is IO divided by I input. So what is your IO? IO is IC, input is IB. But what is IC? IC is beta IB. Okay, so IB will be cancelled out. So our our current gain rather is beta. So it is positive. Why? So it has the same direction as your IC. Okay, so what this implies? So what is beta? Beta is a value, a parameter which is greater than 1. So that means, class, that for common emitter configuration, there is a current amplification. Likewise, there is a voltage amplification. Unlike in common base, we are amplifying only the voltage and not the current. Okay, so what is power? Power is voltage multiplied by current. Okay, so if you have a speaker, how is a speaker being rated? So when you are buying a speaker, uh, you are not after what is the voltage of that speaker. You're not after what is the current gain of that speaker. Usually it is in a form of a power. Okay, so how many watts is that speaker? So the higher the power, okay, the better the performance of your speaker. So common emitter configurations are usually being used as an amplifier. Why? Because it amplifies both current and your voltage. So when your voltage is amplified, your current is amplified, and power is equivalent to voltage times your current. So therefore, power is much, much more amplified. That's why between common base and common emitter is being used as an amplifier. So that's the explanation for that. So we have here an example. Okay, so your beta is 120. Our IE is 3.2 milliamperes. Again, this is in DC for a common emitter configuration. So RO is not being used this time. So it is given by infinite. So we are to determine ZI. So what is ZI? For ZI, we still have to compute for RE. So RE is 26 millivolts divided by your IE. So since IE is given, that is equivalent to 8.125 ohms. However, since this is common emitter configuration, that is not the input impedance for a common emitter. So what's the input impedance? We still have to multiply it with beta, which is 120. So the input impedance for a common emitter is 975. So comparing the two, common emitter configuration has a higher input impedance compared to a common base. So common base is characterized by low input impedance. Okay, so voltage gain is negative RL divided by RE. So we will be using RE only and not your beta RE. So that is negative 2 kilo ohms divided by 8.81.25. So that is negative 246.15. So we have here, your input was amplified by 246.15 times. Okay, so don't forget to write the negative sign here, because if we have no negative sign here, your answer is wrong. Why? Because if you don't have a negative sign here, then we don't have a common emitter configuration. Rather, we have a common base. Okay? Because common base has a positive voltage gain. So, the negative sign is very, very important. So, you will not say it's just a negative sign. No, it's not like that. Because the negative sign implies that we have a common emitter configuration and not a common base configuration. So you have to be very specific with the sign. And then your I input with a 2 kilo ohm load. However, we don't need the 2 kilo ohm load because for a common emitter configuration, your current gain is equivalent to beta, and that is equivalent to 120. So that means your current was also likewise amplified 120 times. So it's very simple. So using another example, using the NPN common emitter configuration, so we are to determine the following. So we have your beta is equal to 80, IE in DC is 2 milliamperes. This time we have an RO. So what is the effect of your RO? So we will be finding that out. Okay, so first is solving for RE. So RE is 26 millivolts divided by 2 milliamperes. So that will give you 13 ohms. And then we have your input impedance. The input impedance is beta RE. So that is 80 multiplied by 13. So that will give you 1.04 kilo ohms. Okay, so for the current gain, you have IO all over I input. So we will be using voltage. So what is this? This is a current divider principle. Okay, so since we are getting the value of your IL, okay, so since we are getting the value of your IL, therefore in our numerator, we have the RO, the opposite resistance, divided by the total resistance and the total current. So what is the total current? That is beta IB. Okay, so that means you have here your current gain, which is equivalent to divide by IB. So what is your What is your IB? So IB will be cancelled out here. So that will give us what? RO plus RL times B. So this is not a new formula, class. We just use a current divider formula here. So since we are trying to measure the current across the load, therefore, our numerator here is your RO. Okay? So therefore, that will give us 77.67. So that is the effect of your RO. It is no longer equivalent to beta, which is 80. So it lowered down the value of your current gain. And lastly, solving for your AV. So we have here now the parallel combination. So why parallel, class? So as you can see, your output is being taken across RL. So the voltage across your RO is equal to the voltage across your RL. So what is the relationship between these two? They are in parallel with each other. So therefore, your voltage gain is RL parallel your RO divided by your RE. So it is negative 89.6. So what happens? What is the effect of your RO? The voltage gain dropped. Okay, so if we have an RO, so the main effect is to lower down your voltage gain from the previous 200 negative 246. Okay, so we just use the formulas. So that is the RE model. So the RE model is dependent on your DC analysis. You have to really start with your DC analysis. Why? Because you cannot solve for your RE. Why? Because you need your IE in solving for your RE. And how are we going to get your IE? So we're going to get your IE rather, in the DC analysis. Okay, so we have the second model. The second model is what we call the hybrid equivalent model. So the hybrid RE model is sensitive to the DC level of operation. Why? Because of the appearance of IE here. Okay, so that result input resistance vary with the DC operating point. So when your DC operating point changes, that means there is a change in your DC current. So technically, there will be a change in your RE. So our second model is what we call the hybrid model or the H equivalent model. So the hybrid means we have a relationship between two different parameters. So this is a combination hybrid. So this is a combination of the voltage parameter and the current parameter. That's why it is called hybrid. So just like in the RE model, wherein we have four important parameters. So what are the four important parameters for what are the four important parameters for RE model? You have the ZI, you have the ZO, we have the voltage gain, and you have the current gain. In the hybrid model, likewise, we have also four important parameters, but the difference is their name. Okay, so since we have here hybrid models, all of their names starts with letter H. So what are those? So we still have an input impedance. So the input impedance is called as HI. Okay, so the subscript I here is for the input. Your E here is for common emitter. Okay, so if we are using common base, you just have to replace with HIB. So the B is for common base. So since we are referring to common emitter, so we will be calling it HIE. Okay, so we have the voltage feedback ratio. So the voltage feedback ratio is HRE. Okay, so we will be dealing with it one by one later on. And then we have the small signal current gain. So current gain is HFE. Okay, F for forward, R for reverse. We will be talking about that one by one later. And then we have here HO. So O is for output. Okay, so the fourth important parameter is the output admittance. Okay, so we have here your HI, we have here your HO, so we have your HR, and we have here your HF. Okay, so for common emitter configuration, we call that HIE, we call this HOE, we call this HRE, and we call this HFE. So for common base configuration, we call this HIB, we call this HOB, we call this HRB, and we call this Okay, so we call this HFB. So this is for common emitter, and we have here common Bs. Ma'am, we are not talking about common collectors. So as we've mentioned before, common collectors is not really used as an amplifier. Okay, so later we will be discussing about that. So hybrid model parameter are defined at an operating point that may or may not reflect the actual operating point of the amplifier. So usually they are given in a transistor specification sheet. So you don't need to solve for the DC analysis. You just have to look for the value for your hybrid parameters. Okay? So this is the hybrid equivalent model. So the hybrid parameters, you have HIE, HRE, HFE, are developed and used to model the transistor. So these parameters can be found in a specification sheet for a transistor. Okay, so let us determine each of the parameter. So we have here your VI. So it is hybrid because we are technically adding. Okay, so when we are solving for VI, we usually add voltage plus voltage. But as you can see, your input here, okay, your parameter here is current, and we are adding it to a voltage. So it is hybrid. You are adding current and voltage, okay, which is you have to add only current, so you have to add only voltage. But since it is hybrid, you are adding both voltage and current. So that means if this is voltage, that means this H11 here must be resistance, because resistance times current is that will give you a voltage or in terms of volts. So that means this H12 must be what? Unitless, because this is already in terms of volts. So we need to add two parameters which are in terms of voltage. Okay, so that is meant by hybrid. So if we're going to solve for H11, we must kill or we must turn off your VO. So how do you turn off your VO? So VO is being turned off. So how are you going to turn off your VO? So usually we short it. Okay, so we short your VO. So if this is shorted, that will leave us with H11 is equal to VI divided by I input. So voltage divided by current, what is this class? This is a resistance. So therefore, H11 is a resistance. So that resistance is called so that is an impedance parameter, and this is called a short circuit. Okay, so this is called short circuit input impedance parameter. So why short circuit? Because we have to short circuit your VO here because this is a voltage source. So impedance, because voltage divided by current will give you an impedance value. So therefore, this is a short circuit input impedance. So why input? Because both of your V and I here comes from the input. So your H11 here is, that means that the numerator and the denominator both comes from the input side. Okay? How about H12? Okay? So H12, how do we solve for H12? We need to make this equal to 0. So how are you going to make this equal to 0? This is a current source. So how do you make current source be equal to 0? You have to turn this into an open circuit. Okay? So when this is already open circuit, then we can solve for H12. So what is H12? H12 is equivalent to VI divided by VO. Now, why H12? Because the numerator is from the input side and the denominator is from the output side. So how do we call this parameter? So this parameter, so this is V1 all over VO. As you can see, this is somewhat a reverse of a voltage gain. So why a reverse of a voltage gain? Because a voltage gain is V output divided by V input, and this is VI all over VO. So therefore, we call this an open circuit. So why open circuit? To solve for H12, we need to open your current here. So this is an open circuit reverse. Okay, why reverse? Because the gain formula here is reversed. Okay? So reversed voltage ratio parameter. Okay? So, why reverse transfer voltage ratio parameter? So, obviously, it is a voltage ratio, but it is a reverse transfer because we have, instead of VO all over VI, we have VI all over VO. Okay? And H12 is unitless. Okay? So, therefore, both voltage will be cancelled out. So let us now go to the output side. So the output side is we have H21 I input, okay, and then you have here your H22, which is in parallel with your voltage. Okay, so in solving for H21, we need to short circuit again your VO. So when this is short circuited, okay, we can solve for H21, and that is equivalent to IO divided by I in. So this is 2, 1 because the numerator is at the output side while the denominator is at the input side. So what do we call this? So this is a short circuit. So why short circuit? We need to short circuit your VO here. So this is a short circuit forward transfer. So why forward transfer? So why transfer? Because we are transferring from the output and the input side. So we have a parameter both on the output and the input side. So why forward this time? Because the formula here is IO over II. And this is the proper ratio for a current gain. So therefore, we have here your forward transfer current parameter. Okay? And then lastly, in solving for H22, we have to open your I input. Okay? And that will give you IO divided by VO. So H22Y, both your denominator and your numerator comes from the output side. Okay? So IO divided by VO. So what is IO divided by VO? So this is the reciprocal of your resistance. And the reciprocal of your resistance is a conductance. So H22 is a conductance. Okay? So what do we call this? We call this a short circuit. So in an open circuit rather, because you have to open your I input here to solve for your H22. So this is your open circuit output conductance parameter. Okay, so what is H11? This is a short circuit input impedance parameter. H12, this is an open circuit reverse transfer voltage ratio parameter. What is your H21? H21 is your forward short circuit forward transfer current parameter. And lastly, your H22, this is your short um, open circuit output admittance parameter. Okay? So, general H parameters for a transistor configuration, usually this is your HI, okay, this is your HR and your VO, this is your HF and your current, and this is your HO. So, your HI is an input resistance, HR is a reverse transfer voltage ratio, HF is a forward transfer current ratio, and HO is an output conductance. Okay, so this is a common emitter hybrid equivalent circuit, and then this is a common base hybrid equivalent circuit. All you have to do is just to transfer or replace B, the E subscript with B. So the model can be simplified based on this approximation. We can say that HR is somewhat approximately equal to 0. So we can replace this by a short circuit. And HO is very, very high resistance on the output. So we can replace this by an open circuit. In this case, we can simplify this like this one. So, does this looks familiar? Okay, yes, because this is also the representation for RE model. The only difference is if this is your beta RE or this is your RE, so this is your beta current. Okay, so usually your beta is also called HFE. So in some specification sheets, you cannot really see beta. Okay, so in some specification sheets, you cannot really see beta. So some of the transistor specification sheets represents your beta with HFE. So when you see HFE, that is also your beta. Okay, another term for beta. So common emitter. RE versus H parameter. So you can see this is your H parameter model and this is your RE model. So your HIE, that is equivalent to your beta RE. So your HFE-IB, so your HFE is equivalent to beta. And then your HOE, if we have HOE, so 1 over RO is your HOE. Okay? So HIE is just the same as beta RE. HFE is just the same as your beta. So for common base, you can see you have here B. So that is equivalent to RE. So HIB is equivalent to RE. HFB, so HFB is, so as you can see, look at the direction of the current. They are not the same. So we have here a negative sign. So that is your negative alpha. Okay? So HIB is equivalent to RE and then HFB is equivalent to negative alpha or negative 1. Okay? So now, we can now relate. So we can now relate your models with our different configurations that we have discussed in the DC analysis. So this is your common emitter fixed bias configuration. So the first thing is you're going to make your capacitor shorted and your VCC be equal to a short circuit. So it is represented by this one. Okay? So the next step is this blue one, this blue transistor here, we're going to replace it with its either RE model or hybrid model. So as we can see, RE is just related with the hybrid model. So the model, the equivalent circuit is just the same. So if you're going to look at the blue one, we're going to replace this blue one with your equivalent circuit. So let us say RE model. So what configuration is this? This is common emitter configuration. So what are we going to do? We're going to make use of your RE model for common emitter. This is the equivalent circuit now. Okay, so beta RE, this is your input, and then your output, you have your beta IB, and then your RO, if you have an RO. So we are now going to include the other part of your circuit. So what are the other part of your circuits? So we have here your RB. Where is RB connected? RB is connected at the base. So where is your base? This is your base. So this is your RB. And then, where is your RO? So, where is your RC? RC is connected at the collector. So, this is your collector. So, this is what we... So, the blue one here is our previous topic. So, these are the model. So, if it is common base, so we will not use beta RE here. Rather, we will use just beta. And then, our current here is alpha IE. But since this is common emitter, so the blue one here is representing your transistor here. And then, you're going to connect the other part of your DC circuit. Okay? So, later on, I will be showing you the formula in getting the input impedance, the current gain, the voltage gain, and the output impedance of the entire circuit. The four parameters that we have discussed, your ZR, your ZO, your AV, and your current gain, is for the blue portion only. So that is the four parameters for the blue portion. So we will still be getting your ZI, your ZO, your AV, and your AI using now the entire circuit. Okay, so that will be our next video. So for common emitter voltage divider configuration, so the same, we will be removing the effect of your VCC and your 3 capacitors. And then, we're what? So, instead of just RB here, we have your R1 parallel R2. So, that is your RI prime. Okay? So, the blue one still represents your transistor here. And then, of course, your RC. So, the only difference is your R1 and R2. Actually, you can make this equivalent to one resistor only. So if we get the parallel combination of this, therefore we will be arriving at a single resistor. Okay. So for common emitter bias configuration, we have what we call unbypassed and bypassed. Okay. So what do we mean by unbypassed? So when we say unbypassed, you do not place a capacitor here. Okay, so you do not place your capacitor here. So if there is no capacitor there, when you replace all the capacitors with short circuit, there is no capacitor that will bypass the effect of your RE. So what will happen? So the figure will look like this. Why? Because the effect of RE is still there. So this is this is the blue portion, this is your transistor. At the emitter side, you have your RE here. Why? Because it's not bypassed. On the next video, we will be discussing what will be the effect if this is not bypassed. Okay? So how about if it is bypassed? So what is the difference? All you have to do is to put a bypass capacitor here. So if we put a bypass capacitor here, what is the effect? It will not, this 0.56 kilo ohms here will not be reflected in your AC equivalent circuit. And what do we mean by that? It will just look like your fixed bias configuration. Okay? So we have here an example. We are asked to determine your RE, your ZR, your ZO, your AV, and AI for both the bypassed and unbypassed configuration. So in this example class, I will be using some formulas that we have not yet discussed, but I will just be using that as an example, and then later on, we will be discussing that on the next video. Okay, so I have here prepared solution for this example. Okay, so I have here a prepared solution for this example. So what do we need here is an IE. That IE will be determined on the DC analysis part. So in the DC analysis part class, no need to bypass the capacitors yet. Why? Because in DC analysis, capacitors just act as an open circuit. So we will be going back with our previous discussions wherein we are not seeing the effect of your capacitors yet. So we will be really starting with the DC analysis. So I hope you can still remember this. So this is our formula for an emitter stabilized common emitter configuration. So we have here your input side. So we are just going to deal with the input side wherein we need to solve for your IE. However, we cannot solve for IE yet. So if we have our KVL here, so we have positive 20 IB. Take note of my subscript. They are capital letters. So why are they capital letters? Because we have here they are dealing with DC analysis. So we have here IB multiplied by 470 kilo ohms. So we have minus VBE minus IE multiplied by 0.56 kilo ohms is equal to 0. However, from our discussions, IE is equivalent to beta plus 1 multiplied by IB. So we can solve for IB, substituting that with our formula. IB is 35.89 microamperes. Okay, so that will give us IE. Knowing IB, we can solve for IE. So IE is beta plus 1 multiplied by IB. So that will give us IE, which is equal to 4.34 milliamperes. So for our DC analysis really is in solving for the DC emitter current. So once the DC emitter current is solved, we can now proceed with our AC analysis. Okay, so in our AC analysis, so in our AC analysis, we solve for your RE. That is 26 millivolts divided by IE. So that will give you 5.99, approximately equal to 6 ohms. Okay, so since this is common emitter configuration, our ZI here is equal to beta multiplied by RE. So our beta from the problem is 120. So that is 120 multiplied by 6 ohms. So that will give you 720 ohms. Okay, so let us first start with the bypass. So when we say bypass, we are no longer seeing the effect of your RE here. So redrawing now, let us now redraw the equivalent circuit. So we have the 470 here, we have the beta RE here, you have the beta IB here, and then we have a given RO which is equivalent to 40 kilo ohms, and then we have your RC here. So looking at the input impedance, what is the input impedance? This is your input impedance. So it is not just beta RE. Rather, we are seeing two impedances in parallel. So what are those two impedances? You have the 470 kilo ohms and your beta RE here. So since they're in parallel, getting the parallel combination of these two, this will be equivalent to 718.9, which is approximately equal to 720 ohms. So since this is approximately equal to 720 ohms, you have to remember this condition class. When your RB or your base resistance is greater than or equal to 10 times your beta RE, we can approximate it to be equal to your beta RE. So in this case, let us say if we satisfy this condition, 10 multiplied by 720, so this will give you 72 kilo ohms. So 470 kilo ohms is much greater than your 10 times your beta RE. That's why we have a ZI here, which is approximately equal to your beta RE. Okay? Likewise, at the output side, what can we see? So we can see an output impedance, which is the parallel combination of your RO and your RC. So getting the parallel combination of your RO and RC, so that will give you 40 kilo ohms in parallel with 2.2 kilo ohms. So getting the product over sum, so that will give you 2.085 kilo ohms. So as you can see, your output impedance is closer to the value of our RC. So when you are when you have two resistances or impedances in parallel with each other, the result is always smaller compared with the smaller than the smaller value. So in this case, it is closer to your 2.2 kilo ohms. Okay? And if we satisfy this condition wherein your RO is greater than or equal to 10 times your RC, we can approximately say that your ZO is equal to your RC. So let us see if we satisfy this condition. What is our RC? RC is 2.2 kilo ohms. So 2.2 times 10, so that will give you 22 kilo ohms. 40 kilo ohms is greater than 22 kilo ohms. So as you can see, we had an output impedance which is approximately equal to your RC. Okay, so we already solved for the two parameters. So two more. So what are those two more? You have the voltage gain and you have the current gain. So the voltage gain is equivalent to minus RC. So just like what we discussed earlier in the common emitter configuration, so we have here your RC multiply negative RC. So why negative sign here? Because this is a common emitter configuration. So RC divided by RE, so that will give you 2.2. Sorry, I forgot the negative sign there. So you have here 2.2 negative 2.2 kilo ohms divided by 6, which is our RE. That will give us negative 366.67. So what do we mean by the negative sign here again? So the negative sign here specifies or signifies that your output voltage is 180 degrees out of phase with your input voltage. Okay? So for the current gain, for common emitter, your current gain is approximately equal to beta, which is equivalent to 120. Actually, the real formula for this is IO all over I input. So beta RB RO divided by RO plus RC, RB plus beta RBE. But if we satisfy these two formulas, okay, so this will just be equivalent to RO and this will just be equivalent to RB. So RB and RO here will just be cancelled out, giving us a value of your current gain equal to your 120. So but if you still want to try substituting the value, so we can see that when you compute this, your answer is just near 120. Okay, so that is the effect if we bypass your capacitor. Now, if we do not bypass your capacitor, if we do not bypass your emitter resistance, that means we didn't place a bypass capacitor across your emitter resistance, your equivalent circuit will look like this. So this will be your AC equivalent circuit. You have here your RE. Okay? So in this case, on the next video, I will be explaining to you why, how this formula has been derived, but we just have to solve first for the 4 parameters. So usually, this Zi here is just equivalent to the parallel combination of a new resistance. We call this Zb. This is the resistance across the base, because as you can see, we do not see only your beta Re here, rather this is in series with your Re here. So therefore, class, we have an additional resistance or impedance, which we will be calling as your ZB, or your base impedance. Okay, so your Zi now is equivalent to RB parallel with your base impedance, and that will give you 58.79 kilo ohms. So in this case, we neglect first. So because of the complexity of the circuit, usually we are neglecting your RC. So if this is open, even your RE will be opened here. So the only resistance that we can see at the output side is your collector resistance. Okay, so therefore, your output impedance is equivalent to RC, which is 2.2 kilo ohms. So for the voltage gain, okay, so the voltage gain, it will become negative RC divided by RE. But take note, unlike earlier, we have here what? RC divided by RE, smaller RE. In this case, class, we have capital RE. So this is the effect when you do not bypass your RC. So when you do not bypass your RC, your gain becomes smaller. So look, this has a negative sign. So this is 3.93 compared to 366.67. That is the effect of not bypassing your emitter resistance. Okay, so it lowers down your voltage gain. And we do not like that. Why? Because we have an amplifier circuit. And what's the purpose of your amplifier circuit? You need to amplify. You need to make your input bigger. So if you do not remove your RE, that tends to have a smaller voltage gain. So that defeats the purpose of your amplifier. Okay? Uh, let's not place RE at the first place. So let's not include RE in the circuit rather. But RE is important in the DC analysis. Why? Because it helps in the stability of your circuit. So it is not very helpful in the amplification side, in the AC side, but it is very helpful in the DC portion because it adds to the stability of your system. So therefore, we place your bypass capacitor so that your RE is present at DC while it is being removed or bypassed at AC. Okay, why? Because it really lowers down your voltage gain. Okay, and finally, we have your current gain, which is 104.99 compared to 120. So it also lowers down your current gain. So from the example, we can see the effect of bypassed and unbypassed capacitor. Okay, so your RE is helpful in the DC analysis while it lowers down the gain in the AC analysis. So therefore, we really use the bypass capacitor. Aside from the fact that it makes your solution harder. Okay? So the equation is more difficult to solve. So therefore, we just bypass it because it's easier to solve. But that's not the main reason. The main reason is the voltage gain. Okay? So we have here a set work. So I will be giving you a set work. So in the school book, I will be placing a drop box so that you can submit the sit work there at the Dropbox. Okay, so this sit work is very easy. So you are just going to draw. So this is more of a drawing of the equivalent circuit. So given these parameters, you are going to draw the common emitter hybrid, the common emitter RE, the common base hybrid, and the common base RE equivalent model. Okay, so this is very simple. I know you can uh, you can draw for this four different equivalent model. Okay, and then we will just be continuing with the we will just be continuing with our last of ace of BJT on the next video. After that, and we're not yet allowed to go back to school because of COVID-19, then we will be continuing with field effect transistors or FET. Okay, so have a nice day. Just stay at home and let's continue praying for this, for everything to go back to normal. So just stay at home and pray, 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 and then study, study, study. Okay, so see you when everything is okay. Have a nice day. Bye.